Okay, so here we go. This topic is about gases. Also, please have out or like open up the file of your equation sheet. I'm going to reference it quite a bit today because there's a lot of equations from this chapter on there. So this entire chapter is about gases. Every single thing is about gases. I'm going to work with a bunch of equations with you guys, and I promise I'm going to give you hints and ideas of how to know which equation to use and where to go from where. So please write those hints down. It's super helpful. A lot of this class is struggling like where to go with the problem. So that can be challenging. So I'm going to be going over that. So let's see. Here we go. Gases. Okay. So, oops, wrong one. So the Earth's three most abundant gases. Ready? Do we know what they are? What's one of them for sure? Anybody? Oxygen. Come on, right? So that's actually the second most abundant. Does anybody know what the first most abundant gas is? Oh, it is nitrogen. Thank you. And then the third one is one you would not likely guess. It is argon. Okay, it is not carbon dioxide, it's not methane, it's not hydrogen. It is argon. Super random, right? All right, so gases have no definite shape or volume. They'll take up any container they can. They have high compressibility, which means they can be like smashed into small spaces. And another word that scientists often use in place of the word gas is vapor. So vapor means gas. So from here on out, if you see the word vapor, it's going to mean the gas state. In physics, pressure of gases or pressure of anything really is defined how much force is being pushed on some amount of space or unit of area. We're not going to talk about it that way in here necessarily, but we are going to talk about pressure. But that is what pressure is, how hard something is pushing on a certain amount of space. Okay. So right here you have these molecules hitting the container, okay, the walls of the container. How often they hit the container and how fast is going to determine what kind of pressure they exert. This substance, this is liquid nitrogen right here. This substance gives off a lot of vapor pressure, meaning it's boiling right now. And you go, oh, boiling is supposed to mean hot. And that is not true. Later on in this class, we'll talk about that. Boiling does not mean hot. Boiling just means something's ability to turn into a gas. And liquid nitrogen turns into a gas instantly at room temperature, meaning it boils. So again, you need to get the whole boiling being hot thing out of your head because that's not what the definition of boiling is. Okay, so in the beginning, they used this closed end barometer, which was done by this Italian scientist named Torricelli. And what he did is he took this container, he put a bunch of mercury in it, and then you have to remember that when you're sitting down, there's pressure pushing down everywhere. Pushes down on you, pushes down on the table, pushes down on your computer, pushes down on the surface of liquids. And so what happened was he put a bunch of mercury liquid. Mercury is one of the only two elements that's a liquid under standard conditions on the periodic table. The other one is bromine. So he did liquid mercury. It's like a metal. It's a silver shiny liquid metal. And the atmosphere pushed down on it, and he saw that the mercury rose up this column, this barometer, okay, is what they called it. And he took a ruler and he measured how high up it went, and it went up 760 millimeters. So he determined atmospheric pressure to be 760 millimeters of mercury because that's how far this went up with the atmosphere pushing down on the surface. Okay, there are reasons why he used mercury. I'm going to talk about the two most important ones. You don't need to know. People always go, well, why don't they use water? Well, mercury is a lot more dense than water, and if you were to do water, the column, because it's so much less dense, would have to be super duper tall, and it would be a pain. And so mercury was just more feasible. Plus, mercury is like silver and shiny, and you can see it easier than you can water, let's say. So it was just a better substance to use than water, for example. Okay, so how tall the mercury column was or how high it rose was considered to be atmospheric pressure from the atmosphere pushing down on the mercury and causing it to rise through the tube. So you have to think of us as like sitting on the ground. We're at like the bottom of an ocean of air. We have all this stuff pushing down on us. That's pressure, which means the higher up you go into the atmosphere, the less stuff is pushing down on you and the less pressure, which is why if you like go up in an airplane, you have to have a pressurized cabin, because if not, theoretically, you would expand until you burst, theoretically, right? Now, if you go down into the ocean, into deep sea diving in the ocean, not only do you have air pushing down on you, but now you have water pushing down on you. So the further down you go towards the Earth core, the more pressure you receive, which is why you have to wear like a scuba suit. If you didn't, the pressure would crush you. It would be too much pressure and it would crush you and it would kill you. So this is kind of a concept to try to I think visualize the idea of pressure, high pressure and low pressure. Okay, so there are some conversion factors. This is 1 atmosphere is 760 millimeters of mercury, which is the same thing as 760 torr, and it's the same thing as 101.3. This is kilopascals. And then this sad little unit down here is PSI. It stands for pounds per square inch, and it's the English version of pressure. Of course, you know, us in England are backwards and we do everything on our own little English scale, like we do pounds instead of grams or kilograms, and we do inches instead of centimeters, and everything's just backwards. So this is our backwards PSI, pounds per square inch. If you were to go to like put air in your bike or air in your car, this is what our tools measure in. We will not use this in here. It's not part of the International System units, SI units. These are our units right here. Now, I just want to have a quick question. Why do you think these two things are the same? Like, where does this torr come from? Does anybody know or want to guess? So we're going to do some math with the conversion factors, which should be kind of like a breather for us compared to what we've been doing. So let's do this. You could probably do them without my guidance. You have conversion factors, convert atmospheres to torrs. So you say 0.357 atmospheres, and then you go look up the conversion factor. 1 atmosphere is 760 torr. You never use conversion factors for sig figs, so our answer will be 3 sig figs. So you get 0.357 times 760 is 71 torr. This one says convert millimeters of mercury to torr. Well, millimeters of mercury and torr are the same exact unit. So it's the same exact number, which is 335 torr. Question so far? Okay, so a barometer is something that we use in like a lab setting. So this thing right here measures pressure, kind of is like a new and improved version of Torricelli's barometer. If you ever listen to the news, they talk about barometric pressure. This is what they're talking about. That's the tool they're using to measure the pressure outside, and it changes whether there's a storm coming in or a high front or a low front. So the pressure on the atmosphere can change. Now, it doesn't change super drastically, but it does change when there's different kinds of weather. Oops. So we're going to do a bunch of equations, and then I'm going to explain to you which one you need to memorize, because I always get that question. Well, which one do I need to know? My answer is you don't need to know any of these individually. I will tell you when we're finished which one you need to know, because you will then know all of them individually. So Boyle's law. No, you don't need to know his name, but you need to understand his law. His law is that pressure and volume are inversely proportional, and an inverse proportion means when one goes up, the other one goes down. So this should make sense conceptually. You take a balloon, you squeeze it and shrink it. That means volume goes down. If you squeeze it too much, what happens? It does what? Pops, right? And it pops because there's too much pressure. So decreasing volume increases pressure. That's an inverse relationship, and it's represented by P1 V1 is P2 V2. So let's go do some wonderful, easy math. A sample of compressed methane, CH4, that's compressed methane gas. I give you a volume and a pressure, and I want your new pressure, and I give you a new volume. Now, because volume is on both sides, I can use milliliters. You can also use liters. There's no reason you can't, but I'm just going to plug in milliliters because it'll make my life easier. So my initial pressure is 503 torr. My initial volume is 648 milliliters. My new pressure is what I'm looking for, and my new volume is 216. So conceptually, they take a container that is 648 milliliters and they shrink it, or they compress it to 216. The pressure is probably going to spike up, so you divide both sides by 216 milliliters, and you get 1510 torr. So it did. The pressure jumped from 503 torr to 1,510 torr. That's a big jump in pressure because they really shrinked and compressed the container. Okay. Charles' law is volume and temperature. So the pressure and volume one is the only inverse proportion. All of the other laws we're about to do will all be direct proportions. So here's how this is gonna, how this one goes. So think about it this way. So temperature is going to be in Kelvin, and I'll talk about why it's in Kelvin in a second. But the reason that, so if you take temperature and you take gases and you heat them up and they move really, really, really fast, they're going to hit the walls of the container more often. If they hit the walls of the container more often and the container is allowed to expand, it will expand because they're hitting it more often. So if temperature goes up, volume goes up, which means if temperature goes down, you lower the temperature of the gas molecules, the volume will also go down. It will shrink, and that's known as Charles' law. Now, temperature has to be on the Kelvin scale, and the reason that is the Kelvin scale is the true zero scale. 0 Kelvin is the lowest temperature possible. It's called absolute zero, and theoretically, it's when molecules stop moving. They've never actually reached it. They've gotten really, really close, but the whole idea is that Kelvin is your zero scale. And a lot of kids forget, they think, oh, 0 Celsius, that's the smallest temperature. And that's not true. There's actually numbers colder than 0 Celsius. 0 Celsius is just when water freezes. There's nothing else special about 0 Celsius. So we use Kelvin in all parts of this chapter. We use Kelvin the entire time in this chapter, no Celsius. You can find out Celsius if you know Kelvin, but you will never plug Celsius into any of these equations. So this is a picture of exactly what a direct relationship looks like. If you move up, the volume moves up. If you move temperature down, the volume moves down, a direct proportion. Okay, so let's do a practice problem. A weather balloon contains 5.30 kiloliters of helium gas, and I give you a temperature, and then I ask for a new temperature in Celsius, and what will the balloon's volume, have increased to 6 kiloliters? So this is V1 over T1 is V2 over T2. So what's V1? 5.30 kiloliters. What's T1? It is not 12. You have to plug in Kelvin. So you take 12 plus 273 and you get 285 Kelvin. All right, V2 is 6 kiloliters. And then what's T2? Now, I did this one on purpose because a lot of a struggle with solving for something in the denominator. You cannot solve for this in the denominator, meaning you can't move the 6 over here and be done. That's because if you move the 6 over here, you are not left with T2. You're left with 1 over T2. So I'm going to multiply both sides by T2 to get T2 out of the denominator because I'm trying to solve for it. And then you multiply by the reciprocal over here, or you cross multiply, however you want to do it. So 5.30 kiloliters comes down here, 285 Kelvin comes up here. Liters cancel, you're left with Kelvin, which should make sense, and you get 323 Kelvin. Now, they asked for Celsius, so at the end, after you have Kelvin, you just have to subtract 273 to get Celsius. Because they ask for Celsius does not give you a right to plug Celsius in here. You'll have to figure out the Celsius at the very end of it. Absolute zero does mean that particles have no average kinetic energy and theoretically stop moving. Yes. Okay. Next. So Avogadro's law. Avogadro's law states that if you have more moles of gas, it takes up more space. This should be very conceptual. So if you have more gas, it takes up more space. If you don't have as much gas, it doesn't take up as much space. It's a direct relationship between volume and N, which stands for moles. All right, so let's try this. Now this one is a little bit trickier. So it says a 13.1 liter sample of ozone or oxygen is held under condition. So this part right here is just telling you that temperature and pressure aren't changing. They're under these, it's going to be under set conditions. So all of the oxygen is converted to ozone. So this is an actual chemical reaction. So O2 is being converted to O3, which is ozone. So this is a 3 and this is a 2. So they give you a volume and a moles of O2, so V and N. So where am I going to do this? V1 over N1, and they want the new volume, but they want it to be ozone. So I have V and N initially, so I'm going to plug those in. So I have what volume? 13.1 liters over 0.502 moles equals the new volume, that's what I'm trying to find, over, how do I find the moles of ozone? Oh, you're going to have to do mole ratios. 0.502 moles of O2. And for every 3 moles of O2 that react, 2 moles of ozone are produced. So that number is 0.33466 something, okay, moles. So you multiply both sides by that to get V2 by itself. Okay, and you end up with 8.73 liters for V2. So let's talk about this. The volume went from 13.1 liters and it shrunk to 8.73 liters. Well, the reason that is because in this reaction you have, 3 of these guys running around. And then when it reacts, though, it drops to 2 molecules or 2 moles of these guys running around. That means there's less gas in the container. Now, not by mass, but by moles. This is 3 moles of gas floating around. This is 2 moles of gas floating around. So if there's less gas in the container, it's going to take up less space. That's why the volume drops. It's Avogadro's law. Questions? Okay, and the last one is Gay-Lussac's law, and his concept is very similar to Charles' law. They kind of go hand in hand, that pressure and temperature are directly proportional, which if you heat up gases, they move faster. If they move faster, they hit the walls of the container more often, therefore exerting more pressure. If you cool down gases, they move slower. If they move slower, they don't run into the walls as often, therefore exerting less pressure. So it's a direct relationship. So again, temperature in Kelvin. So a gas, I give you a temperature and a pressure, so P and T, and then I give you a new pressure and I want to know the final temperature. So P1 over T1 is P2 over T2. So my first pressure is 150 atmospheres over, not 25, you got to convert it to Kelvin, so you add 273 to convert it to Kelvin. My new pressure is 160 atmospheres. I want to know the new temperature. Again, the temperature's in the bottom. I need to get it out of the bottom. Okay, and then multiply by the reciprocal. So I'll do the reciprocal part this time instead of cross multiplying. 298 Kelvin, 150 atmospheres. That's how we get rid of it on that side. 298 Kelvin, 150 atmospheres. So this guy goes away with this guy. Our atmospheres cancel. And we're left with Kelvin, 318 Kelvin. If I would have said Celsius, you would have subtracted 273, and I think it's 45. And, oh, no, yeah, 45. It would have been 45 degrees Celsius. I didn't ask for Celsius. I'm just telling you, if they would have, that's what you would have just had to do that extra step, oops, at the end. Question so far? Okay, so I just told you earlier, the only law you're gonna need to know is this one, the combined gas law. Here's why. If you know this law, you know all of the other ones, because what the combined gas law does is it combines all of those gas laws into one big law. So if they give you pressure and temperature and they ignore moles and volume, meaning if they ignore them, you're assuming they are constant, they are not changing, there's your relationship. There's Gay-Lussac's law, okay? If they give you, if they don't give you moles or temperature, there's the relationship between pressure and volume. That's Boyle's law, okay? If they don't give you pressure or moles, here's Charles' law. This is the relationship between volume and temperature. If they don't give you pressure or temperature, here's Avogadro's law, volume and moles. Again, so as long as you know this one, you know all of the other ones. You just would ignore the other ones. This is the same thing. It's called the combined gas law. This one just doesn't have moles in it, meaning the moles are assumed to be constant. So this one is often referred to as well. Okay? So a sample of nitrogen monoxide has a volume of 72.6 milliliters, so there's a volume, and a temperature, and a pressure. Okay, so I have a bunch of stuff right now. Instead of like 3 things, I have another temperature and another pressure. I want to know what the volume is. So P1 V1 over N1 T1 is P2 V2 over N2 T2. Which variable is not included or mentioned in here? Moles. Beautiful. So what we do is we assume it's constant, and I just like say, whoop, see you later, moles. It's constant, which means it won't change any numbers. And I'm going to use all of these variables. So I wonder if I don't know if I made a, nope, I didn't. Okay, so I'm going to erase this and then plug everything in. P1, my first pressure is 104.1 kilopascals. My V1, my volume is 72.6 milliliters. P1 V1 over T1. T1 is 16 plus 273, so that's 289. Equals P2, my new pressure is 99.3 kilopascals. P2 V2 is my unknown. And my new temperature is 24 Celsius, which I'm not allowed to plug in. That's 297. Oops, this is Kelvin. Kelvin. So I rearrange and solve for P2. So 297 comes up here. Ugh, of course, I ran out of room. 297 comes up. The 99.3 comes down. Now, calculator-wise, I want to talk to you. A lot of kids make mistakes on their calculators plugging this in because they don't use parentheses properly. So I'm going to tell you my foolproof way of doing this. So you'd hit 290. Let me do units real quick. Kelvin, cancel. Kilopascal, cancel. And we're left with milliliters, which is a unit for volume. So calculator trick. Do 297, hit your multiply button, 104.1. Hit your multiply button, 72.6. Then you hit your divide button, 99.3. And then you hit divide again, 289, because both of those are in the bottom. That's the easiest way to get away with not having any calculator issues. And your answer is 75.9 milliliters. Okay. Questions? Okay, so this says, what pressure will be needed to reduce the volume of 77.4 liters of helium at 98 kilopascals to a volume of 60 liters? So look, we have our combined gas law right here. As long as you know that, you go, okay, well, what's mentioned? I have pressure. I have volume. I have a new volume. I want to know pressure. So moles and temperature are not mentioned, meaning they're assumed to be constant. So you pretty much just don't pay attention to them. And then, oh, look, there's Boyle's law. Now, you don't even know it's Boyle's law, but there is your relationship between pressure and volume. So then you just plug and chug from there. Plug and chug. 98.0 kilopascals times 77.4 liters equals P2. I don't know. Sorry, I ran out of room. V2 is 60. Divide both sides by 60. Calculate it out. I need you to give me 1 second. Okay. So again, we're going to go, okay, as long as I know combined gas law, I can figure out any equation that I want to. Here's the unfortunate thing about the combined gas law is that it isn't on your equation sheet, meaning you just have to know it. So look I give a sample of SO2 gas. I have a volume. I have a temperature. I have another volume. That means pressure wasn't mentioned, meaning it's assumed constant, and moles wasn't mentioned, which meaning it's assumed constant. So I'm just going to rearrange this and solve for temperature. So I have a V1 and a T1, but this needs to be in Kelvin, and then I have a V2, and I need to solve for T2. I think I gave myself more room on this one. So I have 1.16 liters over, oops, I don't remember, 23 Celsius. So what's 23 Celsius? 23 plus 273, 296. And then the new volume is 1.25 liters. So 1.25 liters over T2. Again, a variable in the denominator. Multiply both sides so you can get the variable out of the denominator. Okay, so this cancels. And then the 1.16 comes down here, and the 2.96 goes up here. So it ends up being 1.25 liters times 296 Kelvin divided by 1.16 liters, all equals T2. Liters cancel, and these are all 3 sig figs, so your answer is 3 sig figs, and you get 319 Kelvin. Again, if I would have asked for Celsius, you would have just taken this number, and you would have subtracted 273. She tosses her backpack on the table, puffs on a cigarette, and switches the power on. Okay. All right, let's see, next. Okay, so now that we have this big combined gas law, we're going to have something that's called the ideal gas law. Okay. Ideal gas law is going to be, we're going to pretend that all gases behave what's called ideally, meaning they're going to follow all of these assumptions we're about to make in the kinetic molecular theory, and the sole purpose is so that the math is not difficult for us. It makes our life easier. The equation is much easier and user-friendly than what we would have to use if we didn't pretend these things were true. So I want to talk about the kinetic molecular theory. Yes, you need to know these, okay? So this kinetic molecular theory is what allows us to use and pretend gases are ideal, and it's going to give us the gas law equation. 1 second. All right, so in the kinetic molecular theory, we are going to pretend that gas molecules do not attract each other and that they do not repel each other. This will make our life easier. The truth is they do. Gases can attract each other and they can repel each other. If gases become attracted to each other as opposed to zipping past each other and hitting the walls, it's going to mess with pressure. So we try to just pretend like, oh, that doesn't happen, and it'll make our life easier, okay? Combined volume of all the molecules of the gas is negligible, meaning gases are super duper 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 tiny relative to the size of the container they're in. And generally this works. However, if you take a gas and compress it highly and really, really, really shrink the container to a tiny volume, the amount of space the gases make up start to matter, but we're going to pretend they don't, okay? Gases move randomly. This is sort of true. They do move fairly randomly. However, if they're attracted to one another, they don't move so randomly. Or if they're repelled from one another, they don't move so randomly. But they move in all directions and at various speeds for the most part. Okay. When gas molecules run into each other or when they hit the wall of whatever container they're in, we're going to pretend that they have what are called perfectly elastic collisions, meaning they just bounce right back off each other and go about their merry way. Okay, this is absolutely not true. If you went and you ran into the wall, do you think you would lose some energy? You absolutely would lose some energy. And gases do too, but we are going to pretend that they don't because it's going to make our life easier for calculations. Okay. And then this is true that on average, their average kinetic energy, which is their average energy of motion, okay, is proportional to temperature. So you increase their temperature, you increase on average the amount of energy they possess. This is true, okay? So if we did not do this, if we did not do the kinetic molecular theory and ideal gases, anytime we would want to calculate pressure or volume or temperature or moles or anything, this is what we would have to use. It's called the van der Waals equation, and it is the true equation for real gases without making all of these crazy assumptions that we're going to make right now. Okay, it's called the van der Waals equation. It's obnoxious, okay? So, because we're going to follow the kinetic molecular theory and we're going to assume a bunch of things, we're going to use a lot nicer looking equation, and it's going to be called the ideal gas law equation. So, here it is. Looks much nicer. PV equals nRT. This is a lot less crazy than that other equation was. And if you look on your equation sheet, you will see it under your gases section. So here it is, PV equals nRT. And if you forget what anything is, here's the legend to tell you what it is. So P is pressure, V is volume, N is moles, R is going to be a constant, which I'll mention in a minute, and T is temperature in Kelvin. Now, I need to mention two things. The volume in this has to be in liters, and the reason that is because all of our R constant units are in liters, and you don't have volumes on both sides. So they've taken the combined gas law and they made it relative to just one sort of gas for right now. Pressure, volume, moles are temperature, okay? And then if you look over here, you have the R, gas constant R. Now this one we aren't going to use right now. Instead, we're going to call this 8.314 liter kilopascal that's a unit of pressure, mole, Kelvin, okay? This one has joules in it, which is a unit for energy. We will use it later in this year, but we're not going to use it in this chapter. This is another gas law constant, 0.08206 and 62.36. Now, I'm thinking on most of my worksheets, I probably abbreviated these. This is often referred to as 0.0821, and this is 62.4, okay? It is not a big deal. You will be fine whichever one you use. It only changes the number very, 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 very slightly. All right? So if we go back, there is something different about all of these gas constants. So if you look at them, here's the kilopascal one, here's this one, 8.314. This is the abbreviated 0.0821. This is 62.4. What is the unit that is different in all of them? There's one unit that changes in every single one of them.
The pressure.
Pressure. Beautiful. Thank you. So this one is kilopascals. This one is atmospheres. This one is millimeters of mercury. It could be also called torr, right? So if you have kilopascals, use this variable. If you have atmospheres, use this variable. Or not variable, constant, excuse me. If you have this one, use this constant. Now, there are some people and some teachers especially that have you do everything in atmospheres. Now, atmospheres is probably the most commonly used unit for pressure. So what they do is whatever you do, you change your pressure to atmospheres and then you always use this one. That's an option if you like that way, if you feel more comfortable that way, but I'm not going to do it that way because I'm given all these constants, and if I'm given pressure and torr, I'll just use this one, and if I'm given pressure and atmosphere, I'll use this one. But this is possible. You could always convert pressures to atmospheres every single time, and then always just use this one. There's nothing wrong with that. It is a way that a lot of teachers teach. It's not the way I do it, but it is a way that you might see if you're looking up like supplemental videos and stuff. So I'm about to give you a hint now. This says what pressure in atmospheres, so that's ATM, and I give you mole, and I give you volume, and I give you temperature. Now, what is a way you can tell that we won't use combined gas law, right? A big part of this class is being like, okay, I don't know which equation to use. I can plug numbers in, but I don't know which equation to use. Why is this not a combined gas law problem besides the fact I say it's an ideal gas problem up here? Why is it not a combined gas law problem?
It's not changing, so there's not like two different sets of like moles or two different sets of liters.
Beautiful. Thank you, Skylar. So look at combined gas law looks like this, okay? And in these, you usually have like two pressures or two volumes or two temperatures and then one pressure, but like you have like two of stuff. We don't see that here. I see 1 mole, I see one volume, I see one temperature, and I ask for pressure. So that is a hint that it's combined gas, or I'm sorry, ideal gas law. PV equals nRT. So I want to solve for P, so I rearrange. P equals nRT over V. So P equals moles, 18.6 moles. Now, which R do we use? Well, I asked for this in atmospheres, so I'm going to go to my equation sheet and I'm going to look up the R constant that belongs to atmospheres. This is the one right here that has atmospheres in it. So 0.08206 liter atmosphere over mole Kelvin. And then temperature in Kelvin is 318, again Kelvin, right? Divided by volume, which is 12.00 liters. Let's look at units. Moles cancel, liters cancel, Kelvin cancel. You're left with atmospheres, plug and chug, and you get 40.5. I think I actually did 0.0821 on this one, so I think the real answer is 40.4 if you use the unit from your equation sheet. Whatever, I would accept both answers. Okay? All right, Standard temperature and pressure, often referred to STP, is specifically the set of conditions and no other conditions. 1 atmosphere and 0 degrees Celsius, which is the same as 273 Kelvin. This right here is called molar volume. Okay. Standard conditions means like room conditions. This is like more of like what your room is right now. You're probably at about 1 atmosphere of pressure, and it's probably about 25 Celsius or 298 Kelvin if you're not like pumping the AC or the heater. Okay, this is not what a room feels like, 0 degrees Celsius, but it is something that is important called STP. All right, so let's look at molar volume. If you go back on your equation sheet, you have this equation right here. Moles equals mass over molar mass. See, that big M means molar mass. So I can rearrange this that molar mass equals mass over moles. Molar mass is grams over moles. So molar volume is liters over moles. Okay? Liters over moles. Molar volume is V over N. Molar volume. This is going to matter. And if you are at STP, 1 mole of any gas, I don't care who the gas is, occupies 22.4 liters of space. Only under these conditions, though. 1 atmosphere, 273 Kelvin. If you're not at this isn't true. So I just am going to prove to you on the next slide where they got this number. They didn't just pull this number out of nowhere. So this says, I'm going to prove to you that 1 mole of any gas is 22.4 liters at STP. So if you do this, you say, okay, PV equals nRT. And molar volume is defined as volume over moles. So I move the moles over there. And then, in order to get the molar volume by itself, I have to divide both sides by P. So molar volume equals RT over P. So molar volume equals, the R constant is 0.08206. I use that one because the pressure is in atmospheres. Temperature at STP is 273 Kelvin. It's a set number. And pressure at STP is 1 atmosphere. If you multiply this out, guess what you get? So look at the units. Atmospheres cancel, Kelvin cancel, liter per mole. And the number is 22.4. So that's where they got the number from. They plugged in STP conditions into here. Okay? So if you look on your equation sheet, it says ideal gas at STP is 22.4 liters per mole. Remember that -1 means per mole. 22.4 liters per mole. Ideal gas at STP. This is known as molar volume. Okay. All right. So what does this mean? This means 1 mole of any gas at STP right here, up top, is STP right here, occupies 22.4 liters of space, no matter who the gas is. So this is oxygen, this is hydrogen, this is ammonia. They're all at STP, so they occupy 22.4 liters of space. Now their masses will vary. Uh-oh, it's not opening. It's not going to let me draw on it. What is 1 mole of hydrogen gas? What's its mass? Sorry, I can't draw, but you could fill it in. 1 mole of hydrogen gas is how many grams? Well, 2.02, because there are 2 hydrogens. What's 1 mole of ammonia? Well, nitrogen and 3 hydrogens is 17.04 grams. So yes, their masses may be different, but 1 mole of it means 22.4 liters if you are at STP. Well, what else does that mean? 1 mole of anything is what? 6.02 times 10 to the 23rd of that thing. So 1 mole of helium and nitrogen and methane is 6.02 times 10 to the 23rd molecules of methane, and 6.02 times 10 to the 23rd molecules of nitrogen, and 6.02 times 10 to the 23rd molecules of helium, or I'm sorry, atoms, I should say, of helium. okay? But these are all at STP, 1 atmosphere, 0 Celsius, or 273 Kelvin. The only thing that's different is their masses. They still occupy the same amount of space, though, regardless of the fact that their masses are different. Their molar masses are different. Okay? So, this is the last thing we're going to be doing today together. So, I'm going to show you. On your equation sheet, oh gosh, you need to, sorry, hold on one more second. Okay, so what we're about to do is going to be manipulation of Pervner. So if you look on here, you have PV equals nRT, but you also have what N stands for. So in this part of the chapter, we're going to talk about gases in terms of their molar mass. So here's what they did. They took Pervner, PV equals nRT, and they said, okay, well, I know that N equals mass over molar mass. My equation sheet tells me so. So instead of writing Pervner in terms of moles, I'm going to plug this in for moles and write it in terms of molar mass. So PV equals mass over molar mass RT. And it's expected that you can manipulate it this way. Which then means, okay, if I want to solve for molar mass, I just do some algebraic manipulations, right? I multiply both sides by molar mass because it's in the bottom down here. And then, so that gets rid of my molar mass. And then to isolate molar mass, I divide both sides by PV. And then you get this equation. Molar mass is mass RT over PV. That's the equation. So all I've done is I've taken two things off of my equation sheet, plugged one in, and then rearranged. All right? So this first question, it says determine the molar mass. Oops, sorry. Molar mass, that means grams per mole, of an unknown gas if a sample, and I give you mass, I give you volume, I give you temperature, and I give you pressure. So we're talking about gases. So this is likely ideal gas law. Why? I don't see two volumes, I don't see two pressures, I don't see two temperatures. Combined gas law is not going to be helpful. Okay. I see one pressure, one volume, one temperature, and I see grams, and I know I have this equation where PV equals nRT, and that moles on my equation sheet says mass over molar mass, and now I can just plug that into there. So PV equals mass over molar mass, RT, and then I rearrange, I multiply both sides by molar mass, and then I isolate the molar mass, so I divide both sides by PV. So this is my equation. Molar mass is mRT over PV. So at this point, it's just plug and chug. Now you need to be careful. The volume I gave you is in milliliters, and you cannot use milliliters. This isn't combined gas law. You have to use liters because the R constants units are in liters. So other than that, so 0.2, let's see. So this is mRT over PV. That's molar mass. So my mass is 0.290 grams. My R, what R did they give this, or what pressure? That's how you pick kilopascals. So that's the 8.314, sorry. 8.314 liter kilopascal per mole Kelvin. Again, you could have turned that pressure from kilopascals into atmospheres and then used 0.0821 here, but I didn't. What's the temperature? I don't remember. It's 13 Celsius. I don't get to plug 13 into here, so it's 286 Kelvin divided oops, sorry, divided by pressure and volume. So I go back to the pressure, it's 107 kilopascals. And the volume is 148 milliliters, which is the same as 0.148 liters. Let's look at how the units go. So let's see. Kilopascals on the top, kilopascals on the bottom. Liters on the top, liters on the bottom. Kelvin on the top, Kelvin on the bottom. Grams over moles. That's molar mass. Grams per mole. That's molar mass. So I'm going to give you a second to calculate it out. Again, for those two numbers in the denominator, you should hit your divide button twice. It's the best way. Do we get it? So 40.5 grams per mole. Or 43.5, excuse me, grams per mole. Now, there is actually another way to do this problem. I don't care which way you do it. You do the way that makes most sense to you that you could figure out on a test. Anybody know what the other way to do this problem is? So we said molar mass is grams per mole. And in past chapters, we would be like, okay, if we know grams and we know moles, we know molar mass. You can take grams and divide by moles. Do we know grams? Oh, we do. It's 0.290 grams. We just don't know moles. But we could use Pervner to give us moles because N is moles. So PV over RT is moles. And we have all of these. The pressure was 107 kilopascals. The volume is 0.148 liters. The R is 8.314 liter kilopascal over mole Kelvin. The T was it 286, I think? 13 Celsius. So let's look. This times this, hit the divide button, 8.314, hit the divide button again, 286. Kelvin cancel, kilopascal cancel, liter cancel, and we're left with moles. So that number is, let me calculate it out, 0.06, or I'm sorry, 0.00 665,999 something, so 0.290 divided by that whole number is the same thing, 43.5 grams per mole. Either method for this type of problem is acceptable. If you have mass, you can just use Pervner to get you moles and take grams and divide by moles. Or you can do the algebraic manipulation using the equation sheet that's given. You will always get an equation sheet on a test from here on out. You will always get your equation sheet from any test here on out. Questions? We're going to do one more and then I'm going to end. And then I'm going to show you both ways. So I would like you to please try, this is the same exact type of problem. I give you a volume. I give you a volume, I give you a pressure, I give you a temperature, and I give you a mass, and I ask for molar mass. Now the reason I get to ask you to identify the sample is because I was specific of what type of element it was. It's a noble gas, which means you have a bunch to choose from. Otherwise, there's really no way to know who the gas is just by molar mass alone. You'd need more information, like it's a diatomic, or it's a noble gas, or it's a halogen or whatever, okay? So I'd like you to try to work on this. I'm going to work it out as you're working on it, but I'm going to do it both ways. So as you're working on it quietly, I'm going to be working on it quietly too. I'd like you to try to do this based on how we did the last problem. Okay, so that's one of the ways to do it. You get the equation sheet on the AP test also. You get it on the equation sheet and the periodic table on the AP test and on all of my tests as well. So this was the equation manipulation way to do it, where you use pervnert and the moles equation, plug back in, just solve straight out. The other way I'm going to do now, if that's the way you prefer, let me do it in a different color. .378 grams over N. We don't have N, so we'll rearrange. PV over RT is N. The pressure is 88.1 kilopascals. Okay, so the kilopascals cancel, the liters cancel, the Kelvin cancel, you're left with moles. So you have to actually calculate that out, the moles. 88.1 times 0.25 divided by 8.314 divided by, again, 280. This moles is now 0.00946 moles. You take your grams, you divide by your moles, and you still get 40. And then again, to figure out who the noble gas is, you would pull up your periodic table. right here, and you find your noble gas family, it's right here, and you find whoever is closest to 40, and that would be argon. It's 39.95. That's pretty darn close to 40 grams per mole. Whew, how we doing? So that will be it for today.